and inductors in DC circuits. Okay, at the top of your handout it says and AC. I had a feeling as I was working through we probably won't get that done today anyway, so we'll be looking at that next week. There's a link, we need to link between the DC action of inductors and capacitors before we do AC. So we're going to look at capacitors, capacitance and charge. What happens when we connect them in series and parallel. And we'll talk about it. You don't often find capacitors in series anyway, but I'll explain why when we get there. Then we're going to look at the charge cycle of the capacitor and the discharge cycle, what goes on when you switch on and switch off. Inductors and electromagnetic induction, which you know a little bit about because you had a look around that when you've done your science assignment. And then how inductors behave at switch on and switch off, which is similar to capacitors but are different. Alright? So that's the plan anyway. So, capacitors and DC circuits. Unit of capacitance is the farad. Simple capital. People come across the smallest, the biggest, microfarads, 10 to the minus 6, picofarads, and nanofarads of 10 to the minus 9, picofarads 10 to the minus 12. Okay? So, 1 farad is capacitance of 10 to the minus 6, the biggest. Okay? What it is a 1 volt appears when charged to we have a formula there for capacitance where C is the Q, which is the charge, coulombs, and V, potential plate in volts. And we can calculate the charge stored on a capacitor or in a capacitor by current times T seconds, like how long you've delivered that current. So you push more charge. If I so a capacitor, the makeup, in its simplest form, 2 conductant plates, and sandwiched between that are the material, the dielectric. And I've just got some connected leads so we can that is actually, let's make it a bit bigger. That's the first thing. So this is hang on, I'll put something up there, 1 minute. Error plates, more area, more capacitance. So the bigger the area of your plates, the more capacitance you get. Also dependent on the distance between the plates. less distance. So the thicker the dielectric, the less capacitance you get. The thinner it is, the better. And then lastly, the dielectric material. So depending on, for instance, an air dielectric, so just having an air gap would give you much lower level of capacitance than would if you put paper, a thin piece of paper between the plates, and you get paper capacitors. The only place I know of that you'll come across an air capacitor is where you've got a variable capacitor, and they work by having plates that go between each other, so the area it's varying the area. If you go dig in the back of a really old radio, you know them wooden things you used to get years ago, you'll see on the tuning dial there's a variable capacitor, and that's 5 or 6 pins that go within each other and create a variable capacitance. Very low picofarads value. All right. These are the symbols for capacitors up here. So a fixed capacitor, two parallel lines, and then you can have a variable, 2 parallel lines with a line through. Some capacitors are polarized, i.e. they've got a positive and negative terminal. If that's the case, that's indicated on the symbol, and they obviously mustn't be connected the wrong way round then. Typically what's called electrolytic capacitors. So you can't use those types in AC circuits because they won't accept reverse current. As well as the capacitance rating, they also have what's called a working voltage, which must not be exceeded. What generally happens if you exceed the working voltage is you break down the dielectric material that goes short circuit. So if you apply too much pressure, you'll force current through the dielectric and you destroy the capacitor. If that's a paper one, that can be quite explosive in nature. You'll blow the can and spread paper everywhere. So, you know, if you put excessively high voltages on. So you'll buy, like, say, a 1 microfarad 30 volt working. That means you'll get 1 microfarad of capacitance, but its maximum working value is 30 volts. And where you've got to be careful with that is in AC circuits, the working voltage must not be exceeded by the peak. Remember we talked about RMS value 230 on the mains, but the peak value is closer to 300. So you would need working value capacitance of 300 volts working for 230 volt AC mains. Okay, and 600 volt is a kind of standard working voltage for 3-phase 400 volt systems. Are you all okay with that? Yeah? So, got on my next page, before I put all them on the thing. Right. Just put one more page in. Let's try and do this. So, there's our capacitor. Okay, and if we connect that to a source of voltage, I'm not going to put any resistance on there, positive terminal, okay, what happens is electrons, current will flow in that direction, yeah, and we'll end up with positive charges. We get one positive charge, repel, or and on the other plate, we get an equal number of negative charge after a period of time. I'm going to talk about that period of time in a minute. We've got a charge Q on there now because like charges attract, or you can say unlike charges repel. These negative electrons will repel electrons away from that plate, cause the plate to be charged. So action, when we then take the source of voltage away, right, on a perfect capacitor, that charge remains there. We put 10 volts on, and then take 10 volts away, after that are charged up to 10 volts, then when we take the source away, that'll sit at 10 volts. Now a good capacitor will hold that a long time, but eventually it will leak away through the electric. Alright? So that's one safety point you should be aware of. If you've got a capacitor in a 400 volt AC system, that could quite easily, depending on when the supply was switched off, be charged up to about 560 volts when you turn the system off. And they'll give you a nasty. So if you ever work on anything where there's capacitors, speed controllers are a prime example. When you take the cover off, if you're unsure whether that's discharged, they do try and make sure they discharge, then find a fairly large value resistor and just touch it across the capacitor and give it time to discharge. They normally do on inverters, as when the supply goes off, they automatically let a small relay drop out that connects in a discharge resistor. And usually on the front cover, the ones I've seen, it says, do not remove cover until this LED goes out, and you'll see that LED gradually fall away as the capacitor's discharged. Once that's gone out, it's safe to open the cover. You do need to be careful of them because they hold charge. Alright? Yeah. All happy with that? Right, in your calculations handout, you've got these problems, I believe. Example problem 1. Not that one. I'm going the wrong way now. On that. So the voltage, determine the voltage across the 4 microfarad capacitor when charged with 5 millicoulombs, and find the charge on a 50 picofarad capacitor when the voltage applied to it is 2 kilovolts. Right? About 5 minutes to have a go at them. Right. Problem 1, A. How have you gone about that? What formula were you using? C is equal to Q over V. So we've got to find the voltage. Q over C. And Q is or 5 times 10 to the minus 3 if you prefer it that way. Divide that by 4 4 times 10 to the minus 6. 1250 volts. Alright. And then B. Formula. Q is equal to CV, yeah. So that's 50 times 10 to the minus 12 for peak currents. There was times 2 times 10 to the 3 for kilovolts. Which is 0.1 micro coulombs. Q equals IT. And I is 20. No, hang on, that's not time, is it? Times 3 times 10 to the minus 3 equals. And anywhere. Equals 1.2. That can't be 10 to the minus 9. 3. Yep. And then find the voltage between the plates. V is equal to Q over C. That's 1.2 times 10 to the minus 3 over 20 times 10 to the minus 9 equals, I've got 600 volts. You're right, yeah, it's 12. Which means that must be 6,000 then. It's 10 times bigger. Just check. Three fours are 12, so that's got to be 12 times 10 to the minus 3. If you still get 600, then that must be what I put in my calculator when I... Not having a good day at the moment, am I? 600, is it? Yeah. There we go then. To show you how something like this board plan up can throw you off track. Right. Okay with that. Fairly simple anyway. So. Right. So capacitors connected in parallel. If we connect capacitors in parallel, C1, C2 and C3, like we've got there, if you think about it charging up to a particular voltage, let's say 10 volts, not really thinking about anything, we'd have the same number of charges on each of the positive plates because they're in parallel, so they're all going to get the same voltage. So we'd have the same number of negative charges on there. So they're all going to charge up to the same voltage. The charges on them, Q, may not be the same because they might not have the same capacitance value necessarily. But they're all going to charge up to 10 volts or 20 volts, whatever we're applying. Yeah. So the total charge must be, the total charge stored must be each of the charges, Q1, Q2 and Q3 added together. And if you add more capacitors in parallel, then you're going to get more added on. All right. So if in that terms, the total capacitance that you've got in that circuit when you parallel up three capacitors must be C1 plus C2 plus C3, and we can carry on. So if you remember, capacitors are opposite to what resistors are. Resistors in series we add together, capacitors in parallel we add together. Yep. So if you want to know the total, just add them all up. One thing to be careful of, if they're all microfarad values, 10 microfarad, 15 microfarad, 50 microfarad, we can just add the numbers up and the answer's in microfarads. The problem comes if you've got 2 microfarad ones and one in nanofarads or picofarads. You've then got to be careful to apply the power of 10 notation to each of them to get a proper answer. So if they're all in the same multiple, it's easy. So you might want to convert them all to the same multiple to make it easier. But whichever way, if they do vary between nano, pico and micro, then you need to take that into account. All right. So if we look at capacitors connected in series, that's a whole different kind of ball game, right? So if we think of it in terms of resistors, they're not resistors, but if we connected 3 resistors in series, we would share out the voltage between them by Kirchhoff's voltage law. Yeah. So dependent on their size, they'll all get a share of that voltage. So if they were all the same value, then they'd all get the same voltage. All right. However, it's a bit more tricky working out exactly what goes on, and there are reasons why you don't very often see capacitors connected in series, because I'm going to draw that out a bit bigger like I've done my diagram before. Back to black. And we connect that to some kind of DC source. Well, that's the positive terminal, that's the negative terminal. Yeah. Now, if we think of this plate here on the outside becoming charged up with 6 positive charges, yeah, what that's going to do down on through this conductor here is going to draw electrons of equal number to that plate, which is going to leave this plate positively charged. Remember, between these plates is a dielectric, so no current can flow. If that's a perfect capacitor, no current can flow from there to there. Yeah, these electrons are coming from here through this wire here and onto that plate. Yeah, which is going to leave this plate negatively charged. Yeah, which is going to make this plate positively charged because it's going to electrons have been drawn away from it, and then lastly the outside plate how many positive charges and negative charges associated with the total charge involved in that circuit? The total charge stored. How many positive, how many negative charges equals the total? How many, when I take, think about when I take the battery away, right? So let's say for a minute that I take the battery away, right, and connect in the discharge resistor. How many electrons are going to flow through that resistor to reinstate the normalized charge, no charges on the plates? How many electrons are going to flow? It's only these ones that can go anywhere, isn't it? They can, and these positive charges, that's the only usable charge on that circuit. Because when you discharge it, these electrons are going to go back to that plate. Those are going to go back to that plate. They're going to flow through that resistor. Any work. So the charge on the outside is the total charge. But if we say we've got Q1, Q2, and Q3, total charge on the outside, the total charge is Q1 is equal to worth of charge. As soon as you see capacitors connected in series, you can work out what the total capacitance is. We have to do that in a minute. From that you can get the total charge. From that you know the charge on each of them. Always the total charge on each capacitor has to be. Otherwise you've got an imbalance and current will be flowing. What you'll see what happens in a minute. All right, I want to leave it for a minute, because if they're different values, they'll still have the same charge on them, but the voltages will be different. Yeah. But the interesting thing, as you'll see, is the biggest voltage goes across the smallest capacitor. All right, and you'll see that in a minute. So do you all kind of get that? And that's not an easy concept to get, but the way we calculate, I got my next slide. No. So I'll do another one. So in essence then, the way we calculate total capacitance in series remember that? But from resistance, that was for parallel resistance. Yeah. So if that's C1, C2, and C3, and we can add any number we want in parallel. Yeah. We get the total capacitance by doing the power minus 1 formula, I like to call it. Yep. So let's give them some values. 10 microfarads. CT is equal to brackets. 10 to the minus 1, they're all microfarads, so we ain't got to worry about powers of 10. 20 to the minus 1 plus 25 to the minus 1, all to the minus 1. Do that calculation for me, please. Okay. Now, how do we calculate the total charge? QT is equal to CT times V. Right, so if we say we're going to apply 10 volts, that is 5.26 times 10 to the minus 6 times 10. 260 microcoulombs, I hope. Yep, everyone agree? That's the total charge. Now, that total charge is on each of those capacitors. Yep. Everyone's got the same charge on it. So, now we can find the volt drops V1, V2, V3. So we'd say QT on each capacitor. Therefore, VC1 is QT over C1 that is 260 times 10 to the minus 6 over C1, 10 times 10 to the minus 6. .6 volts. No, that's C times V. That's this bloody board there. That's meant to be a dot for multiplication. VC2 something don't look quite right here to me. Hang on. Just summarise that because we had a lot of messing around with the board. If we get these in parallel, the same charge, we know there must be the same charge on each of them. So we can, if we calculate the total capacitance, we can then use that to find the total charge. In this case, 52.6 microcoulombs. Then we can apply the total charge, 52.6 microcoulombs, to each capacitors in turn and work out the voltages. So the 10 microfarad has got 5.26 volts across it. The 20 has got 2.63, and the 25 has got 2.104. So it's interesting to note that if the biggest capacitor has got the least voltage to hold the same amount of charge. Does make sense if you think about it. But the one point about these in parallel is that all these in series, because all three would need to cover the full working voltage, because if that middle one goes short circuit, you're going to share the voltage out between two. If two of them go short circuit, that one remaining capacitor is going to get all the voltage. So if that's a 30 volt circuit, they all need to have working voltages of 30 volts. You won't see it very often. The only time I personally know of it using it is to make up values you haven't got. If you want a 50 microfarad, you ain't got one, but you've got 200s, you can connect them in series and get exactly 50. So you can use series network to make up values that you haven't got. But other than that, I don't normally deliberately put capacitors in series. I put them in parallel to get more bigger capacitance, but not in series, not intentionally. That doesn't mean that you don't get series capacitances build up in a circuit because of what they call stray capacitance. If you think about it, right, if you think about it carefully, two conductors, there's a piece of copper, there's another piece of copper, right, each of those has got insulating material around the outside of it. Not a very good capacitor, tiny little capacitance between those two conductors, right? But remember this thing with frequency. The higher the frequency, the lower the impedance of a capacitor. Therefore, as you get up to higher frequencies, these even if you do high gigahertz, 2 tracks on a printed circuit board with its insulation between them is like a tiny little capacitance that can affect that circuit at really high frequencies and can need to be taken into account. Frequencies, kilohertz, doesn't matter. It's negligible. Alright? But you won't normally find deliberately capacitors connected in series. No. But you could say you're using resistors in series as a you use it as a voltage divider, but it's not a transformer in that sense. Because if you say you're going to use a voltage divider to divide the voltage down, you've got no isolation between the two sides, and also you're wasting power because all the dissipation in that other resistor is not being used for anything. Alright? So they're completely different things. So, there's 2 more examples. One of capacitors connected in parallel, one connected in series in your calculation handout. Have a go at those, please. Right, gents. I just can't get nothing to work right on this stuff today. So I've got my answers document up. So, example 3, total charge is the equivalent circuit capacitance. Let's add them all up. So they're all in microfarads. So then 1 plus 3 plus 5 plus 6, 15 microfarads. Is that what you got? Yeah. And then we can do the total charge is equal to the total capacitance times the total voltage. and that came out at 1.5 millicoulombs. All got that answer? Yeah, I ain't gone wrong anywhere this time. Good. I didn't put a deliberate mistake in. And then the parallel one. So total capacitance, use the formula. I've got the 1/over form of it here, but that's just similar to what you've done. You should get 1.714 microfarads. So your answer is, you've got what I got. Yeah, because you've got, look, in my answer, it's 1/over CT is equal to 7/12. So CT is 12/7. That is the right answer. Yeah, that's fine. It's the same thing. Have you done to the power of -1 after you close the brackets? Otherwise, all times this is by little VC. Little VC with instantaneous voltage at a always equal time in the time of the transient period. I always add up to 10. So if it's switch on, it's not on the capacitor, it must be 10 across the resistor. All agree with that? Yeah? And if that resistor's got 10, that's 10 ohms, then must be 1 amp flow. So my little blue dot for there, that's 1 amp. We've got two different scales on the y-axis here. I've just made the highest current a little bit lower than the highest voltage so we can graph more than one thing on the same axis. Okay? So that is at time t is equal to 0. Yep, all happy with that. Yep, no dissenting voice. So, if we consider the situation that's the position that's on. So if we move on in time a little bit, no particular amount of time at this stage, okay, but let's say we're moved on to the point where there's 7 volts across the capacitor. If we're going to carry on obeying Kirchhoff's law, that must leave 3 volts across the resistor. Yep. And therefore, we've got a 10 ohm resistor, 3 divided by 10, 0.3 of an amp as flowing. So I've tried to change that information onto my graph over here. Okay. Here we go again. If you tell me about it. Yeah, so our current has dropped from its initial state down to 0.3 of an amp. So I've just estimated that where I put the dot. Okay, your capacitor voltage has risen from 0 to 7 volts, and your resistor voltage has dropped from 10 to 3 volts. All right, all in the same amount of time. Yeah. If we then go on another small amount of time until the capacitor's got 9 volts across it, and therefore only 1 volt across the resistor and 0.1 of an amp flowing. The rate that this charge goes on is reducing all the time, because you're trying to push these electrons onto that plate, and because there's so many on there, I don't want to go so much now. That's the way I like to think of describing it. So it's not a linear situation, it's non-linear in action, it's not a straight line. So again, we've got a drop in our current, the blue one, from 0.3 of an amp to 0.1 of an amp. We've got a further rise in the red capacitor voltage to 9 volts, and on our resistor voltage there's now a volt only. Okay. If we carry that on further in time, what happens is the capacitor voltage rises up towards its limit of 10 volts, the voltage that we're applying. We can't go any higher than 10, okay, and the resistor voltage tends towards 0, and I say tends towards because in theory it'll never actually get there. The bit that isn't got there is so small that you can ignore that. 0, okay, and the current eventually stops flowing because the capacitor is completely charged. Right? So that's what happens during capacitor charging. I'm going to put this slide up now. Okay, you haven't got this in your notes, but you'll be able to get this stuff down off Google anyway. Alright, I'll put the capacitor voltage and the current on there, because essentially the resistor voltage is always going to follow the shape of the current anyway. Alright, so I'll put that dashed line on there. What that dashed line is, if that's the initial rate of capacitor voltage rise. What that does is that where it meets here, if it hit there in that amount of time, okay, that would do that if we carried on delivering the 1 amp to the capacitor. So instead of the current dropping, if we done something electronically, so we carried on applying or kept 1 amp flowing by increasing the voltage, we'd hit that 10 volts in that amount of time from there to there. That's called the time constant. Greek letter tau. Yeah, where tau, the time constant, is equal to C times R seconds. Right? Now, that constant is repeatable. Every time you charge that capacitor, 0 volts with 10 volts, but the same amount of time to get to that point there, and then to get to the next point and the next point. That charge time in completion is repeatable, commonly used in simple timing circuits. Alright, so that'll repeat the same over and over again with the same resistor and capacitor values, of course. Alright, and you'll see why in a minute when we do some calcs, but capacitor is considered fully charged after 5 times CR, 5 time constants. Right, what you're 99.99% charged, we consider as full. Alright. Now, I'm going to go on to a summary page that's got formulas for these functions. They are a mathematical function. The capacitor voltage, top left, rises to its limit of whatever voltage you're supplying it with. So if you apply a constant voltage, you'll always get that shape. It's called an exponential rise to a limit. That limit being the number we put in front here, Vs, in this case. Okay? The way that works is, this bit, e to the power of minus t over the time constant, is always worth a little bit. So there's always 1 minus a little bit, so therefore that bit in the brackets can never equal 1. And therefore you can never actually, in theory, reach the full applied voltage. Which is what, the first assignment? Science? Yes. You had some functions similar, yeah, but you didn't, yeah, you used an equation like that, yeah. Okay? Your current starts at maximum current, V over R, and falls away exponentially towards 0. But that bit you multiply I by is always worth a little bit, so in theory it never actually reaches 0, but it gets so close after 5 time constants that we consider it to be fully discharged. And the resistor voltage starts off at 10 volts, falls away, again tending towards 0, again after 5 time constants. Alright? Yeah? So we're going to have a look at a problem now around the capacitor charge. That is this one. So, a 20 microfarad capacitor that's connected to the 50 kilo ohm resistor, and the circuit is connected to a 20 volt DC supply. I'm not going to attempt to draw that circuit on. Normally I would with the board how it is today. I'm not going to even bother. Alright? So, first of all, I, the initial value of current flowing. How do we calculate that? Yeah, because the initial current is always going to be the highest current. At switch on, we've got the full voltage across the resistor. So that's V over R, that's 20 over 50 times 10 to the 3. .400 microamps. I'll put on my thing 0.4 milliamps. Yep. Actually, you'd probably 400 microamps, wouldn't you? 400 minus 6. 400 microamps, not very much. Why do you think I've chosen a high value of resistor in this example? What's it going to make quite? It's going to charge up slowly or slowly. The time constant is going to be quite high. So B, time constant. Tau is equal to C times R. That's 20 times 10 to the minus 6. 50 times 10 to the 3. I think you should get round up. Alright? All happy? Yep. So, what we want now is the instantaneous current, so it's little I after 1 second. I at 1 second. What that means is equal to the maximum current, which is the initial current, isn't it? Times e to the minus t over the time constant, c times r, or tau. You can either use CR there or you can use tau, it doesn't matter. Alright? Our current was 400 times 10 to the minus 6. We'll multiply that by e to the power of minus 1 over 1. We're finding out how much voltage we're charged up to after 1 time constant. Sorry, what current we got flowing after 1 time constant? If you push the button with ENG on your calculator, that'll put it to the nearest multiple of 3 power. So what do you got now? There's a button called ENG. Yeah, times 10 to the minus 6. Yeah, because that's what we really want it in an engineering multiple. Yeah. So have you found your ENG button? Yeah. If you push that, that'll move it to the nearest suitable, and shift will move back the other way. So you can go up and down them if you want. If you keep pushing it. So what was that? 1.147.2 times 10 to the minus 6 amps, or 147.2 microamps. Yeah. So after 1 time constant, the current has fell from 400 microamps to 147.2. Yeah. That's after 1 second. That's after 1 time constant. All right. D, the instantaneous voltage across the capacitor after 1 second. So we were looking for VC after 1 second, and that's equal to Vx 1 minus e to the minus t of a tau, because that's exponential rise to a limit. Yeah. which equals 20 volts for an iron times 1 minus E to the minus 1 over 1. One second. Okay. Well, let's do it for 1. I want to do it for 1. There's a reason. I want to do it after 1 time constant. Yeah. Just do 12.64 over 20. Yeah. So it's gone 0.632 of the way, or 63% of the way from 0 to 20. Yeah. There's a reason why I want to do that. Now calculate it for 2 seconds. Adding a little bit to this question. So VC after 2 seconds, VS 1 minus E to the minus 2 over 1. I've done how far that's gone towards going the whole distance from 0 to 20. It's a ratio. You'll see what I mean in a minute, right? It's gone 63% of the way. Yeah. .29 volts. Yeah. What that'll be, that's now risen, so what I'm trying to point out is that'll have moved, what that'll have done is gone another 63% of the gap towards, so it's going to reach 6, if you put 10 volts on, that'd reach 6.32 volts after 1 time constant. And then that'd go another 63% towards the top after another time constant. There's the same space each time is what I'm trying to point. So you can see that the rate of increase has gone down. Yeah? We've gone 12 volts first time, and then we're only gone another 5 volts after the second time constant. Okay? In F, that shouldn't say the 2 seconds, where it says voltage 2 seconds, cross the 2 seconds out. Wrong. So part F is the value of the capacitor voltage after 5 time constants, or 5 seconds in this case. So I'll leave you to finish that off now. Part E, we're looking for the time it takes for the resistor voltage to reaches 15 volts. So it starts at 20 and it falls, remember. Yeah? So little VR is equal to Vs times E to the minus T over tau, the time constant. Alright? Now, we need to rearrange that formula so that we got T equals something. How can I go about doing that? How do I rearrange that formula so that I get T on its own? Yes, a good start. What were you going to say, Jake? Yeah, the LN will come in a minute. Yeah, you're on the right track. We've got to get rid of VS first, because if we apply LN at the moment, we'd have to apply it to VS as well. Yeah? So you're going to get VS over this side. Little VR over VS is E to the minus T over tau. Then, Jake, what are we going to do? Apply the natural log to both sides, because that will cancel the E out, yeah? So, as our operation, ln both sides. So with the ln on the side, I'm going to, so ln of VR over VS is equal to minus T over tau. Next, yeah, multiplied by tau. So I'm going to bring minus T over this side because that's where I want it. Tau times ln little VR with a big VS. And how do I deal with the fact that T is negative? Multiplied by minus 1. So T is equal to minus tau ln little VR over VS, close brackets. Now we can put our numbers in. That is minus 1 times ln. We're looking for when the voltage is 15 volts, when it starts at 20, equals. Not the same as doing the power minus 1 though. Yep, 0.288 seconds. When you know the time constant is 1 second, does that look right? If the capacitor is going to rise by close on 7 volts in one time constant, the resistor voltage must fall close on 7 volts in one time constant. We're looking for less than 7. We only fell 5 volts. It takes less than a second. Alright. And then the last bit is just to show, calculate the capacitor voltage after 5 time constants, 5 times CR, just to show you how close it is to the full 20 volts.